All right, let's progress to sorting algorithms. And first off, we're going to be looking at merge sort. All right, so let's look at why we need to sort any kind of data. So we use sorting algorithms to sort any kind of data. That could be numbers, letters, words, anything like that. And an example we can think of if we're trying to find a number in a list, so we're searching for a number, right? And if you remember, the last video we went over was binary search, and we know that binary search is the best algorithm for searching for a number or letter or any kind of data. So I'll give a link to the video now. But in order to use binary search, we do need to have our data ordered, right? That's one of the prerequisites of binary search, is having our data already ordered, already sorted. So we can use the most efficient sorting algorithm to do this, and that would be this one, merge sort. All right, so what are the steps to accomplish merge sort? So first we're going to split our data in half, and we're going to keep splitting until all the elements are on their own or they're in their own list. So we can see that in the diagram on the right, we have our big list at the top, and then we split it into two. 7, 3, 2, and 16 is now a sublist, or a smaller section of the list. Then we split that into two again, to 7 and 3, and we split it again to 7 by itself, and then we have 3 also by itself in a separate sublist. We then compare each element to its neighbor. So then we're going to be comparing 7 and 3, and if is 7 smaller than 3, it is not. So we rearrange them, or we split them, and then we group them together, and the same process happens for all elements. So we do this with all sublists until there's only one list remaining, and that is our final outcome of the sorted list. So if we go into a little bit more detail, we're going to be using an approach called divide and conquer. If you haven't gone over this before, I've got a video, I'll link it now. And it's basically the process of decomposition, right? So we're breaking a problem down into smaller, more manageable parts, and is also a method of a top-down approach, because we starting with a big problem, we're splitting it into loads of little problems which are more manageable, and then combining again. That's where the saying goes: divide, conquer, and combine, and that's exactly what we're doing here. So dividing each list in half until each list has only one element, that is 7 being the one element, or 3 or 2 or 16, we can see in the middle. And then the sublist is then sorted, and this is where the name comes from, and merged together until only one list remains. Right, so in summary, this is the most efficient sorting algorithm. The time complexity is O n log n. If you are a GCSE student, you don't have to worry about this, but if you're A level, it's a good thing to have in mind. We can see that the purple line is the merge sort big O notation time complexity of O n log n. We can see that as we put more data into the algorithm, the number of iterations or operations or steps, you could say, that the algorithm does is fairly linear. It's a fairly straight line. Well, not compared to the actual linear, which would be O(n), but compared to another algorithm like bubble sort, which I'll be going over, is the O(n squared, which is the blue line. We can see that the purple line is a lot more efficient, and that's why we tend to use merge sort most of the time. Merge sort is more complex, and that does have advantages because it is more efficient, as we say, but it is harder to implement. Whereas if we compare it to a more simple algorithm, it is not as efficient, but it is easier to implement or easier to develop or code. All right, so I hope it helped. See you next time.